welcome to this channel Chemistry Made by Dr. Ashok Mulik. We were discussing this molecular orbital theory, and last time we have seen the general information regarding the application of this molecular orbital theory to heteronuclear diatomic molecules, where we have seen that the energies of atomic orbitals like this, which are helping us in different manner to bring out or consider the interaction between the atomic orbitals of different elements. On the basis of this, we are going to see some examples of these heteronuclear diatomic molecules. The first example is carbon monoxide. So here carbon is one atom and oxygen is different atom. Their properties are different, their electronegativity characters are different, and because of this they are showing different characteristics in the molecular orbital diagram. Because of their electronegativities, their contribution to the molecular orbital varies. Further, we should know that when the difference between the energies, like this energy that is sigma of symmetry and pi symmetry, or sigma and this sigma star, if we consider the various molecular orbitals say of S nature, means 2s, 3s, etc., and of P nature like this 2p, so they are expected to interact with each other. The energy difference between them should not be more than 12 electron volts. So if it is so, means if the difference in their energies are more than 12 electron volts, then they cannot interact with each other. Means there is no interaction, so the S and P characters remain separated in the molecular orbitals. But here the interaction is also helpful, or it plays important role in determining the various characteristics, whether that is the polarity of the bond and contribution of the participating atomic orbitals or atoms in order to develop their polar nature, and also they represent their reactivity with other molecules. So reactivity is also important factor which depends upon the electronegative nature of the participating atoms. So because of their difference in electronegativity, carbon is positively charged and oxygen is negatively charged. Now here you will find that the carbon monoxide is having the symmetry around z-axis. So if we say this is z-axis, then they are showing C infinity V symmetry. So they are having infinite number of rotations having the same symmetry. Another thing is Px and Py, which are lying perpendicular to this z-axis, are showing C2 with symmetry, C2 V symmetry. So depending upon their symmetries, they will show interactions with each other. Now if we see this molecular orbital diagram, you will find that these are the atomic orbitals represented here for carbon. So we have represented these atomic orbitals, means we are considering only the valence shell, not the inner shells like 1s. So we are considering here 2s and this 2p for carbon. So they are having such a large difference. Similarly, you will see here the atomic orbitals are shown here for the oxygen atom. So this is the 2s and 2p orbitals of oxygen. Now here the electropositive atoms are having their atomic orbitals with relatively higher energies compared with the same energy levels of electronegative atom So energies of these atomic orbitals of electropositive atom like carbon are higher compared to the energies of these atomic orbitals of more electronegative atom like oxygen. And these energies means comparatively we are saying that the energies of carbon are higher and energies of atomic orbitals of oxygen are lying lower of the same symmetry. So that is why they are not lying parallel, which we are seen in case of homonuclear diatomic molecules. And that is why we are saying that these are heteronuclear diatomic molecules. So we have shown the electrons present in the valence shell of these carbon atoms. Carbon atom has total 6 electrons, out of which 2 are present in 1s, 2 are present in 2s, and 2 are present in 2p. So this is the electron distribution of carbon. Similarly, oxygen has in all 8 electrons, out of which 2 are present in 1s, 2 are present in 2s, and 4 are present in 2p. Okay. Now, then this 2s and this 2s is 2s of carbon is and 2s of oxygen, when they are interacting with each other, it shows that the 2s is closer to this molecular orbital. So after linear combination of this 2s and this 2s, they are producing this bonding molecular orbital and this antibonding molecular orbital. So bonding is called 2 sigma G and antibonding is called 2 sigma star U. So see, this is 2 sigma star U. This is 2 sigma star U. Or we can simply show here 2 sigma and 2 sigma star. This is also meaning that this is sigma star U and this is 2 sigma G orbitals. Similarly, here you will find that the atomic orbitals of these 2p of carbon and oxygen, the atomic orbitals of oxygen of matching symmetry will interact with each other or undergo linear combination, and they will produce the pi molecular orbitals, and this is sigma molecular orbital. So this is sigma molecular orbital. So we can show here this sigma as 3 sigma G. So we are showing this as 3 sigma G. So we can show here this 3 sigma G, 3 sigma G like this. So pz orbital of this carbon from 2p and pz orbital of this oxygen will undergo linear combination to produce this sigma molecular orbital. And px and py of carbon and px and py of this oxygen will undergo linear combination to produce these pi molecular orbitals of bonding nature. So we are represented as pi 1, pi 1. So one is obtained from px linear combination lying parallel to each other. Similarly, another pi 1 is obtained from linear combination of py which are also lying parallel to each other. And we are considering here Z as the internuclear axis. So pz undergoes linear combination giving this 3 sigma G molecular orbital. And the px py orbitals undergo linear combination to produce this pi 1 star and pi 1 star. So there are 2 pi 1 star orbitals. One is resulting from px lying parallel, and this is like resulting from py linear combination which are lying parallel to each other. So it gives the antibonding molecular orbital. Then pz of this and pz of this undergoes linear combination to produce antibonding molecular orbital 3 sigma star or you can say 3 sigma u star, same. So this is about the formation of molecular orbitals. Now we can see here the shapes or contributions. So here you will find that this sigma, this 2s orbital of oxygen is energetically closer to this 2 sigma g bonding molecular orbital. So this atomic orbital is converted into this sigma g bonding molecular orbital because these are energetically closer. Means this molecular orbital has more contribution of this 2s of oxygen and less contribution of this 2s of carbon. So here you will observe in this diagram, this carbon atomic orbital has less contributed, whereas this oxygen molecular orbital has more contributed. So it bears the more characters like oxygen atomic orbital, that is of this 2s, and it has less characters of this 2s of carbon. Similarly, you will find here this sigma, 2 sigma u star. So it has shape like this. So here you will find that the 2s of carbon. So this portion, the portion of this side of the nucleus is representing the contribution of molecular orbital resulting from carbon, and portion to this side shows the contribution of oxygen. So here you will find that the electron cloud of this molecular orbital is larger of this carbon and smaller of this oxygen. So means here antibonding molecular orbital has more contribution of this 2s of carbon and less contribution of this 2s of oxygen. Again, here you will find that these 2p and these 2p are undergoing linear combination to form these pi molecular orbitals which are lying lower. So compared to this 3 sigma g, the pi molecular orbitals are lying lower. It means there is such a large difference. So this difference shows that the S and P contribution, means these molecular orbitals have S and P characters, and this is because means this is shown by this higher energy level of 3 sigma g and low lying pi molecular orbitals. So these are having the B1 B2 symmetries, and they are having representation of 1 E1 orbitals. 1 E1 orbitals. Then, so here the contribution you will see here is also having like this. Means they are lying parallel to each other. So here you will find that these pi bonding molecular orbitals have the larger shape, larger electron cloud contributed by these 2p, px and py. So this side of this diagram, so here there will be the nucleus like this, or center of the xyz coordinates. So this portion is contributed by oxygen, 2p orbitals of pi nature, and this portion means half of this is contributed by carbon molecular orbitals of pi nature, pi orientation. So this is the representation. So these orbitals are lying one above the other. So one orbital has say negative sign of wave function, another orbital has positive sign of wave function. So they are lying one above the other, and these are lying one beyond the other. Say this has negative sign of wave function, then this will have positive sign of wave function. So you can compare like this. One lobe, this is one lobe and this is another lobe. So they are lying one behind and one in front side. So this 1b2 is having shape like this or orientation like this, and this one B1 has orientation like this. So you can identify their shapes like this. So here you will find that this sigma 3G, 3 sigma G has contribution like this. So this side represents contribution by carbon. So here you will find that the carbon has larger contribution, and this has, this side has small, shorter contribution by oxygen. So contribution of this oxygen to this is relatively smaller, and this contribution of this carbon is relatively more here. Then you will find that this B1 and B2 symmetry, antibonding molecular orbitals of pi nature. So they are having the shapes. So they are having also shape like this, but they have different lobes like this. They have different lobes. So they are having say plus sign of a function. Lower green lobe has minus sign of a function. This upper green lobe has minus sign of a function. Lower say red colored lobe is plus sign of a function. Similarly, B2 has the front lobe of say plus sign of a function. Back side lobe has minus sign of a function. And this another lobe, that is plus sign of lobe. Here it is minus, here it is plus. So in this way, this has say plus sign of your function, this has minus sign of your function. So in this way you can compare. So they are lying apart from each other. So like this. So you will observe that, or you can say like this. So they are showing, or they are moving away from each other like this. They are not coming closer because their signs of wave functions are different. These lobes are moving away from each other. So in this way you can imagine this B1 and B2. So this 4A1 has also antibonding nature. So the contribution to this 4A is more from carbon. That is PZ of carbon. So it is shown in larger size. And contribution from this oxygen is relatively smaller. So they are shown with relatively smaller size. So here, so this is about molecular diagram, and these are the shapes. Now you can find here this another diagram showing molecular orbital diagram of photoelectron spectrum. So this shows photoelectron spectrum of carbon monoxide. So here you will find that the values are shown on this side, which are representing the energies of these energy levels. So these energy levels are correlated. Energy level of this 3 sigma G is correlated to this peak, which is appearing in this photoelectron spectrum of carbon monoxide. So the energies are like this: 14 electron volt, 16, 18, 20. So the value is increasing in downward direction. So this has B2 symmetry, and they are resulting in the form of sigma G. So these are A2 of pi nature. These are sigma G of X. So here you will find that these two are representing sigma peaks, and this is representing the pi peaks. So pi peaks are shown in are arising because of these pi 1, pi 2 molecular orbitals. So you will find here the characteristic peak of these photoelectron spectra arising due to these pi molecular orbitals. So which is fine. So the peak is of fine nature. It is split into fine lines, but this is not splitting into more lines, that is fine lines. There is larger single peaks. So these are indicating the sigma characters. So this is representing this peak. So we have shown in the same line. So you can point these lines together. So the larger peak and this pi 1, pi 2 is lying in the same energy level. So we are comparing here, or we are correlating this photoelectron spectrum of carbon monoxide with the molecular orbital diagram of this carbon monoxide. So from which the application of molecular orbital theory becomes more and more clear. So we will stop our discussion here, and we will see the next point in the next molecule in the next lecture. So please subscribe to this channel and press bell icon and like button also. So thank you very much for watching this video.